No, that's the number 3 one.
Oh yeah, I remember you giving us details about
Yeah.
class.
Because the number 2 one is going to be, it's not just programming. It's similar to the one you just did, where there's like a bunch of math problems and then some light programming.
Yeah.
But the final project is all programming. So that's why I'm like, I should post that sooner rather than later, so that you can get started on it. Now that if you are currently in the Python class, then you're at a point where it's like mostly done the term, so you're probably working on projects or whatever. So that was the idea. So anyway, though, on that note, I did post also assignment 3, like the chapter review one. I checked the course outline, and this is funny. When I was calculating the due dates, because they asked me to do that at the start of the term, and I'm like, I don't know when my stuff's going to be due, but sure, I'll slap this date down. I forgot to account that we lose Mondays for class. So technically, the outline says it's due this Saturday. No, it's due next Saturday, because that seems unreasonable when we're finishing the topic today. So,
What is that?
it's like there's like 4 questions. It's the chapter review assignment that's just like, so it's like the other assignments you've done, the sort of like slightly more involved quizzes. That I think I posted last night, question mark or something. It was probably at like midnight, so that still technically counts as yesterday. We'll say that. But anyway, yeah, I thought that one, the course outline says it's supposed to be due this Saturday. No, it's due next Saturday, because nobody's going to complain about an extension, I don't think. So yeah, that's due next Saturday, and it's posted. The big programming group assignment also posted. I have all of the instructions on what you're supposed to do. The first 3 questions on it, I've given variations of in the past, and they were fine. Everyone found them fine. So you don't have to, like, that one shouldn't be like too brutal or anything like that. And you've kind of done one of them already, so it's just extending your code. But the last one is the binary search tree that I was talking about. I have instructions in the assignment, but also on Blackboard, there's a zip file which contains some templates for code. There's a file called bst.py. That's the one that you need to build, and then there's details on what you need to do and all that. So that's the one that's going to be more involved. If you know what a binary search tree is, it's like, if you're very coding experienced and know about binary search trees, it's like a few hours of work. It's not too bad. You just have to think about it. But if you're still a novice and still getting your head around it, it will be more challenging. So just, again, letting you know. So anyway, let's finish up our topics. So we had last class. All my pens are dying. That's great. We did some basic probability stuff. What is probability? What are some common pitfalls with probability? And then I did end on a fun note, kind of. I did the Monty Hall problem, the doors, the simulation. In retrospect, it would be a lot more fun if I covered this entire section in terms of simulations and stuff. That would be more fun, where we're actually working in Python to test these probabilities and stuff. But, well, that's retrospect. Sometimes it kicks you in the face. So unfortunately, we're still doing it good old-fashioned on the whiteboard. We also talked about conditional probability. So that is this concept here, probability of B given A. And there's just a formula for it, thankfully. So this is when we're sort of restricting our possible options here. We're saying, hey, okay, we know A happened. Let's only consider B under the assumption that we're looking at stuff from A, right? A is an event that happened, so we're narrowing our focus down to that. So I have a specific example here. Oh my goodness, my pages are all mixed up. I can't count. There we go. I got it. I did it. Okay, so we have the following example. So suppose you're traveling from Toronto or from Edmonton, it doesn't really matter, I guess, to Toronto, with a connecting flight in Calgary. I mean, many of us have taken this type of flight where you're flying out of Edmonton and you stop in Calgary and you're like, why though? The reason why is because suffering with flights makes it cheaper. Okay, so the probability that your flight leaves on time is really bad. Probability of 0.2 or 20%. I think someone made up these numbers and it wasn't me. Again, statistics textbook. So if the flight leaves on time, well, the chance that your luggage goes with you, probability of your luggage arriving with you is 0.75. So 75% chance, which again, I don't think that's pretty accurate because I've taken lots of flights and I've only ever had my luggage misplaced twice. So again, made up numbers. If it's not delayed, then this probability is 0.5. That makes sense, right? If your connecting flight is delayed, then the chance of your luggage getting misplaced, not necessarily misplaced, not arriving with you is way lower, right? Think of it this way: your transfer flight was delayed, and they're like, sorry, we couldn't get your luggage on there on time. It's on the next flight here, right? Like that's pretty common in flight delays. So we have a couple of questions we want to answer. We want to know what the probability of arriving with our luggage. I'm going to use shorthand here. We want to know this probability, the probability of our luggage arriving. We also want to know the probability that our first flight was delayed, given that our luggage did not arrive with us. So in terms of conditional probability, this is you're standing at the airport and you have no luggage with you, and your friend is there to pick you up and is like, oh, you don't have any luggage. Flight was delayed. And we're asking, how likely is that for you to say, yes, it was? So when we're dealing with conditional probability like this, I like to sort of draw what I would call like a sort of tree, right? You've got your thing here, flight leaving, sort of your first event. So it's either on time or it's not. So the chance of it being on time is 0.2, right? The chance of it being delayed, well, the chance of it being on time is 0.2, so the chance of it being delayed is 1 minus that. So 0.8. Okay, so now that our flight has happened, our second event that we're interested in is the chance of our luggage arriving with us. So either our luggage arrived with us, or it didn't. So in each of these cases, if our flight was on time, we know that the probability of our luggage arriving with us is 0.75. So that means it not arriving is 0.25. If our flight was delayed, though, the probability is 0.5. So since these are events that happen in sequence, your flight is on time or delayed, and then your luggage either arrived with you or it didn't. We multiply these probabilities together when we go across this tree. So we're asking, what's the probability of our luggage arriving with us, right? Independent of whether or not it was on time. So we either get to that path by going from on time to luggage or delayed to luggage. Right? Those are the two situations where our luggage arrived with us. So it's on time, and so we multiply our luggage arrived with us, or, and this is what I'm saying, multiply and add, or our flight was delayed and our luggage arrived with us. And so this gives us the chance of our luggage just being with us regardless of whether our flight was delayed or not. And this is apparently 0.55. So, okay, now we want to answer the second question, this conditional probability question. So delay given that our luggage was not with us. There's a formula for this. And no luggage over probability of no luggage. So, okay, well, we actually kind of have this second one, right? This no luggage, because we have the probability of luggage. So it's just 1 minus this, right, would be no luggage. Now this one, probability of delay and no luggage, we just go down the path. So delay, no luggage. 0.8 times 0.5. And this gives me whatever number it gives me, which, there we go. So that means if you're standing there and saying you have no luggage and someone says, oh, how likely was it that you were just delayed? It's 89% given the probabilities we have. So that means someone without luggage probably had a delay in their flight, is what this really means. Now we can ask a question. Are these independent from each other? And we kind of touched on this, right? Is luggage arriving independent from delays? So we have a formula for this. The definition says, oh, the probability of, what is it, delay? Yeah. Needs to equal the probability that we just found. Well, we know what this is, 0.8. And we just found this thing, 0.889. They're not the same thing. So the definition of independence from probability is that these are the same thing. These are not the same thing, so we would say they're not independent, but that matches up with how we would intuitively think of independent events, right? Just think of the human experience of anyone you've ever met, or just people talking to it, or movies. People frantically running for their delayed connecting flight probably lose their luggage more often, right? Or have to deal with luggage being lost. So that matches the intuitive idea of what independent events are, right? That obviously those two are related, right? Okay, that's what I have for probability right now. So we're going to start talking about counting, combinatorics. So counting. So when we say counting, we obviously don't mean like 1, 2, 3, 4, 5 on your fingers, right? That's not what we mean by counting here. So when we're talking about counting, we mean for extremely large situations, right? So if you have say, a password, right? How many possible ways can I form this password or something like that, right? A really, really big thing. That's what we mean by counting, right? Or a very hyper-specific set of circumstances, right? You want to know how many outcomes are there. That's what we mean by counting. Big things. So we want to develop some techniques just to do that. And we're not going to spend too much time on this because it is high school review. If you don't know this, well, we're not going to spend too much time on it, so it's fine. It's just sometimes you might need to count, like if you're doing a loop and you're like, how many iterations of this loop do I need to do? You might need to do some basic counting techniques to figure out how many times to do that. So I have a bunch of descriptions here in my notes, but for multiplying, it's very similar to probability. So for multiplying counts, we're looking for the keyword and generally, right? And, but we need independent events. So an example would be you're flipping a coin and you're rolling a six-sided die over here, right? Those are unrelated to each other, right? The outcome of the die roll does not depend on the coin you flipped over here, right? They're independent of each other. So if we wanted to figure out how many possible outcomes there are, well, there's 2 choices for the coin, 6 choices for the die, so 2 times 6, right? 12 possible outcomes that you would write down. So that's what we mean here. If the events are independent from each other, then we can multiply them together. The key word here is we're usually looking for the word and to describe multiplying probabilities. So for adding, again, it's sort of or. We're looking for mutually exclusive events. So need mutually exclusive events. So generally this will be or. So an example that I have written in the notes is, say I'm going to a bakery, right? I'm buying one item from the bakery. They have 7 choices of bagel flavors and 13 choices of donut flavors. So there are 20 total choices for me to make, right? 7 plus 13, because I am one or the other, right? It's not choose a bagel and also choose a donut. It's choose a bagel or a donut, right? So we add them up. This matches our definition of probability, so that's why I'm not spending too much time on it. I have a bunch of, like, it's a half a page of more explanation of this, but this is the gist. So let's do an example of some basic counting techniques. So in Alberta, we have license plates on our vehicles. So there are 3 types of license plates. There are more than that, really, but 3 general license plates. That you could just go in and buy, not counting vanity plates because those can be pretty much anything. So we've got regular plates. And there are sort of 2 situations for regular plates. So 3 letters, then 3 digits. We can also have 3 letters, then 4 digits. Except when we're talking about these letters, there are only specific ones they can be, or rather there's ones they can't be. They can't be A, E, U, or Y. So we also have veteran plates. So veteran plates start with the letter V. Then 2 letters. Then 2 digits. And then there are motorcycle plates. So these are, I have to check because I don't remember, 2 letters and 3 digits. Okay, so these are sort of the situations that we can generally talk about with license plates. There is one extra thing though. No license plates can have O or I, right? And that's kind of obvious why they can't have O or I, because is O a 0 or an O? Is I a 1 or an I? From a distance, it's hard to tell, so we just say don't include those. Okay. So we're going to count the number of possible license plates. So for these first plates here, they look like this. Right? There are 3 letters, then 3 digits. So we're excluding those 2, O or I. There's 26 letters to choose from, minus those 2, so there's 24 possible choices for each of these. Right? Now these are digits, so there are 10 possible choices for these. So that means all told, this license plate format has 24 to the power 3 times 10 to the power 3 choices, right? We multiply all of these numbers together. Right? And that gives us one of these license plate patterns. And then we can do this one. Same thing, except we're excluding 4 different letters here, right? We're actually excluding 6 total, so there are 20 choices here. And then each of these digits can be 10. Or not 10. There are 10 choices for these digits. So 20 to the power 4 times 10 to the power, 10 to the power 3, like that. So that's how many license plates we get there. Now we got to deal with these ones, the veteran plates. So starts with the letter V always, so we don't have to count that, right? It always starts with V. Now we have 24 letters. 24 letters, 10 digits, 10 digits. So this is 24 to the power 2 times 10 to the power 2. There aren't that many veteran plates possible. And now we have these motorcycle plates. So there are 24 letters and 10 digits. And so we multiply all that together. 24 squared times 10 cubed, right? So now, these are all the different formats of license plates that we have. And all of these are sort of mutually exclusive, right? You have either this type assigned, or this, or this, or this, right? So we add all of these together. And I mean, it's some big number. We'll write it down. So it is 9457600. So it's pretty big. 94 million possible license plates in Alberta. So the reason why we would care about this, right, is, well, we don't want to run out of license plates, right? That would be bad, right? Imagine going to the registry and you're like, oh, I want to register my new vehicle. And they're like, sorry, we're out. Like, we're sold out of those. We don't have any more. Not good. So we ideally want to have lots of possibilities for license plates. But this is like quite a lot. So that's why some people will have the same license plate for a very long time, right? Someone will be like, oh, I've had the same license plate 50 years, right? Well, that's because even if you do that, we're not exactly in danger of running out of them. But also, even if we were, just add another digit to the end, and now we get like this I think is 80 million or something like that. Add another 10, another digit to the end, and now we have 800 million out of it. So like, just an extra digit is going to add a lot of possible license plates, right? So The point is, there are a lot of them, right? We're probably not going to run out of license plates anytime soon, even if literally every person in Alberta had like 3 cars. Well, maybe not 3 cars, because these don't really add that much. Like I think the veteran plates is like 56,000. This is like 560,000. So it's like less than 1 million are these. So really, it's these two that are contributing a lot of license plates. So most people are able to get license plates. So this is sort of a basic counting technique that you would. This is the type of technique that you would probably use if you're looking at programming and you're like, okay, well, I need to run this loop some number of times. How many times do I need to do it? Well, if it's not variable based, then you would probably need to do some kind of counting argument like this, right? Like figure out all of the possibilities and then sort of count them out, multiply them together, add them up, and be like, okay, it's 5,620 or whatever, right? That's how many iterations of my loop I need to do. All right, cool. All right, or when you're figuring out so it's not really a problem with Python array sizes. You don't need to pre-allocate arrays. But if you're working in something like C, you might need to know how big your array is before you assign to it, and you don't want to go outside of the bounds. You can't add to it at the end. So that's where something like this would come into. So point is, this counting stuff is not completely out of nowhere, right? It's not just for nothing's sake. There is a reason for it. But there are another couple things related to counting. So one of them is a permutation. So a permutation is an ordering of distinct items in a line. So generally speaking, with permutations, we care about the order. So something like this in a license plate, ABC is a different permutation than BCA, right? Those would be different startings of license plates. We would not count those as the same thing. So the total number of ways to order our objects from n total is, there's a formula for it. So it's n factorial over n minus r factorial. Which, there's a button on your calculator that does this, right? NPR. Okay, so an example of where this would come up. Suppose 35 other people attend a conference with you. And 6 tables seat 6 people. So, you got 36 seats, you just got a bunch of tables and people can sit at them, right? So, you want to sit with your 2 friends or colleagues or whatever. How many seating arrangements are there? Right? How many possible seating arrangements can we make? Well, this is essentially a permutation question because we look at ourselves and we're like, okay, first, if I'm going to sit at this table, I need to figure out how many ways there are to arrange my friends and I, right? There's 3 of us. So arrange friends first. So we've got our row of friends like this. So you choose one of them, myself included. So there's 3 of us, pick one of them. There's 2 left that haven't been picked yet. And then 1 more after that, right? So this is 3 factorial. So there's 6 ways to do this. Okay, so now that you've arranged your friends, we need to say, okay, well, what's left, right? There's still 3 seats left at this table. So now, choose 3 people. No, hold on. Let me rephrase that. Choose an arrangement of 3 people from the remaining 33. So there's actually 2 ways to think about this one. And this is why permutations are kind of de-emphasized conceptually, is we do have this formula, right? This is choosing an arrangement of 3 people from 33. Well, number of ways to order 3 things from 33. Well, that's exactly what we're computing here. So we do have this formula over 33 minus 3 factorial. So 33 factorial over 30 factorial. You can figure this out. But there's also another way to think about it. It's that we're choosing 3 people from the remaining 33, so we can argue in the exact same way as here. So there are 3 seats remaining, or rather, we need to choose an ordering of 3. So for the first person, choose one of the 33. Now there are 32 people left. Choose one of the 32 left, and then choose one of the 31 left. Right, but these are the exact same numbers because this ends up being 33 times 31, 32 times 31, which is some big number, 32736, which is the same thing as that, right? So, okay, cool. So then that means the total, well, I arranged my friends, and then I arranged these people, 736, so 6 times 32,000, whatever, right? So we could see where this would be relevant. If instead of this formulation of the problem, you just had, 100 people, you might want to maximize the number of seating arrangements, right? So how many tables do I put out with how many chairs? You ask yourself, okay, I want to maximize the number of seating arrangements, so that increases the chance of people intermingling, right? You could put one table with 100 seats at it, which, okay, there's not very many ways to arrange people around that, so there's not going to be much intermingling. You could also put 100 seats down, but again, same problem. There's not very much intermingling, right? You have like a neighbor, that's it. So, it's somewhere in the middle, right? Some number of seats at some number of tables will give you the most amount of people who kind of interact with each other, or most possibilities for that. So this is a question that would answer that. However, there is a concept that comes up way more often, to the point where we actually have a special notation for it, and that's the idea of a combination. So sometimes we don't care about the order. If we don't care about the order of our selection or our line, we can instead find the number of combinations. So this is a permutation, this is a combination. So this is the number of ways of sets of our items we can make from N. So in this case, looking back at the license plates, A, B, C, and B, C, A, it's the same set, right? It contains those three letters, A, B, and C as letters, right? So we would count these as the same thing now with this formula. So it's almost like the permutation one, except we have an extra, thing on the denominator there. What this is essentially saying is, okay, figure out all the ways to order the R things from n total. That's this formula. And now divide out all of the ways that we can order those things. Right? So this is basically saying there's some number of way to organize these letters, right? In this case, there's 3 letters and 3 ordering, so it would be, 6 total things. And we're just going to divide out by that, right? This would be 3 factorial here. On your calculator, this says NCR, which you've probably seen on if you have a TI-83 or something similar. You've seen this symbol. But in terms of math, we actually have another notation for it, which we would call N choose R, right? This comes up so the place where you would have seen it briefly in high school, maybe not phrased in the way I'll phrase it, is the binomial coefficient. A plus b to the n is the sum from I equals, is it 0? Yeah, it should be 0. To the n choose R, or I guess I'm going to use the R. Don't worry about what I'm writing here. You don't need this. I'm just saying this is somewhere where you would have seen it. A to the R, b to the n minus R. So this is called the binomial expansion. This basically tells you, you've got a plus b squared. We know that's a squared plus 2ab plus b squared. It tells you how to write this, right? Given any power, right? It just tells you all the numbers that go in front. This number right here also comes up to something called Pascal's triangle, if you've heard of that. So this number, it crops up a lot. But Pascal's triangle just tells you, hey, a number here, there's a relationship between its numbers above it. You can calculate numbers below by doing a relationship with the numbers above. But the reason why we care about it is it gives us sort of this counting technique. So useful for counting cards. Counting, not counting cards in the gambling technique is cheating, but counting hands. So an example would be poker, right? We've got a bunch of different hands that you can make in poker. You can get a pair is a valid hand. It's the worst hand. If you just say, I got a pair, that's it. Well, at least it's something, but it's the worst. And then on the other end, you've got a royal flush. That's the best hand, right? That's the best possible hand you could make. And these are essentially ranked in likelihood of them showing up, right? There's 4 royal flushes possible, 1 in each suit. That's it. That's the only way you can make that hand. For pairs, though, there are a lot of pairs, right? A ton of different pairs. And then you could imagine, well, 3 of a kind is less likely, 4 of a kind is pretty unlikely. Full house is also kind of unlikely. Straight flush, unlikely. And essentially the scoring in poker or the winning hands are just dictated by their likelihood, right? What's more likely to have happened. And then if they're equally likely, then it's just based on the face values of the cards. So let's just demonstrate what I mean here. I could show you how to make, 3 of a kind, 4 of a kind, full house, straight flush, that sort of thing. And all of these techniques will tell you the likelihood of those hands. And then you just compare them all. You just make a table of all the hands. You just order them from least likely to most likely. And there you go. That's the poker hands. So if you don't know, poker is a game played with a standard deck of cards. So that's a 52 card deck. There are 4 suits, diamonds, hearts, clubs, and spades. And those cards have face values. There's ace, 2, 3, 4, up to 10, then jack, queen, king. So 13 faces in each card. And there's 4 total suits. And in poker, you're dealt 5 cards. We're talking 5-card stud here, not like Texas Hold'em or anything like that. So 5-card stud, you're dealt 5 cards. You try to make a hand, right? And there are specific combinations of cards that count for winning. So one of those is 3 of a kind. So when we're trying to make 3 of a kind, we just have to think, well, how could we possibly approach this? Well, one of the things we can do is first, we pick our kind. So that's the face value of our card. So there are 13 face values. And from those, we just want to pick one, right? We're going to select one of those. All right, so 13, choose one. Right? We don't care about any ordering here at all, right? In this case, we're selecting one from a group of 13, so we're only getting one thing, so ordering doesn't really matter here. Permutations and combinations with same result here. But because when we're talking about card hands, we don't want to call, ace then king a different hand from king then ace, right? So that doesn't make sense to use permutations. It's the same hand, right? It's the same value, essentially. So first we're going to pick our face value. Then, from that face value, choose 3 cards. Right? Because what we're saying is, all right, we've got our face value. We've chosen that face value. From that, we've got 4 cards, right? There's 4 of each face value, right? 4 5s, 4 6s, 4 aces. So from that face value we just picked, there are 4 things to choose from. We want 3 of them. We are going to select 3 of those cards. And that gives us our 3 of a kind, right? Okay, but there's still 2 other cards to pick for a valid poker hand, right? So now, choose our last 2 cards. But we need to be a bit careful here, right? So first we've got our chosen face value, and from that we've chosen 3 cards. And so now what we want to do is we want to say, okay, well, let's choose from the remaining 12, we're going to choose 2. Okay, but we actually want to make sure that these 2 cards are distinct from each other, right? So the quote unquote naive thing here would just be say, okay, well, actually just what I wrote there, right? We don't care. Just choose 2 cards. But the problem here is we have not omitted the possibility that they are the same. Because with just this alone, we're saying, you know what? Ace and ace would be fine, right? We just chose 2 cards at random. That's totally okay. But we actually do care about that, specifically because we're talking about 3 of a kind. And in poker, there is another hand that is 3 of a kind and then a pair. It's called a full house. That is actually a better hand than 3 of a kind. So we want to make sure that we're not doing that, right? Because that is a different hand. So what we're going to do is we're going to say, okay, we've chosen our 3 of a kind. Now from what's left, choose 2 cards at random. And from those, there are 4 choices for one of the cards, choose one of them. And then there are 4 choices for the other card, choose another one of them. You don't care which one. Right, so choose a face value and then choose 3 of those cards. Now, from what's left, choose 2 of those face values. And from those face values, grab 1 card each. That's what this is saying. So it turns out this is 600, nope, wrong one. There it is. Oh God, I don't have the number written down. I have the final probability. This is some number. You can do it in your calculator if you want. But the reason why we would care about this in poker specifically is we can use it to figure out the likelihood of getting this hand. So how likely are we to get three of a kind? So this right here is just number of hand, which on its own isn't super interesting. What we want is probability. So that's number of desirable outcomes, or number of hands that we actually care about. So three of a kind, full houses, etc. Number of winning hands, or I don't want to say this, chosen hands, over number of total hands. So that bottom number, so this top number is whatever that is. So what's this bottom number? I'm just gonna write down 13, choose 1, 4, choose 3, 12, choose 2, 4, choose 1, 4, choose 1. So now we need to figure out number of total possible hands. Well, that's relatively easy, right? There are 52 cards in a deck of cards. Choose 5 of them. Right? If we're looking at all the total possible number of hands, it doesn't have to be a good or valid hand, right? It just has to be a hand when it comes to counting. So this gives us 5 random cards from all 52. So this is the number I have written down. 88 out of 4165. So this tells us that three of a kind is relatively unlikely, but not super unlikely, right? Like it's possible. So what about four of a kind? We can do a similar argument. So same thing, we say, okay, from the 13 possible face values, we got to choose one of them. Don't care which one. So ace, 5, 7, who cares? Now, from what we just chose, there are 4 cards. We want all 4 of them. Right? That's what that's saying. Now, for our last card, there are 48 remaining. Just choose one of them. Who cares? Does not matter, right? Because the only thing that matters for a 4 of a kind hand is we grabbed the 4 of a kind. Over, same thing, 52, choose 5. And this is apparently 1 over 4165. So this makes sense. This is telling us that 4 of a kind is much less likely than 3 of a kind, which, I mean, that makes sense, right? In this case, we want just the 3 cards have to be the same. This is saying 4 cards have to be the same now. That's a lot harder, right? If you've played poker, you know that's harder. So this kind of makes sense. But the general idea here is going to be the same for doing poker hands. And spoilers, the quiz I have you do basically, I'm leaving this here so that you can have it. It's find a full house instead of a 3 of a kind, and it's very, very similar argument. You say, okay, well, I need to choose my 3 of a kind, which we did here, but now I want to choose a pair. So that's 12, choose 1, and then you choose 2 of the cards, right? So it's a very similar argument for full house. Straight flushes and the flushes and the straights are a little more awkward to figure out, but a similar kind of argument will get you there. Anyway, I don't want to spend too much time belaboring this because, again, it's if you took 30-1 or 30-2 here, you covered this a lot. Like, just this symbol right here from high school. How many times did you press that on your calculator? Like, a lot, right? I remember my diploma exam there was so much combinatorics on it. It like the multiple choice was mostly combinatorics, it felt like. So you are well versed in pressing that button on your calculator. So in this class, you will have to press that button a few times for one question, and then move on. So that's kind of why I'm looking at this and I'm like, yeah, I could probably make this section more fun by making it like more of a simulation based thing. It's just like, I kind of came to that conclusion as I was going through it this time. So you're not the guinea pigs on that at the moment. So you got the old fashioned lecture on a board style for this one, but there's lots of fun simulations you could do. Like, hey, make a card simulator or something like that and use it to figure out possibilities for basically you could enumerate every possible poker hand with a computer, right? There's not that many. I have it written down. There's see, this is 2.6 million possible hands in poker. So that's a lot for a human being to think about. But you know what it's not a lot for? A computer. So you could actually calculate these odds. You know, you do the formulas or whatever, and then you actually run a simulation on your computer to find all the possible hands, like literally enumerate every possible three of a kind. And then you would see that they match up, and it's like, oh, cool, I can do that. And then it shows you the power of simulation techniques, right? You can actually simulate a hand now and see how likely it is, yada, yada, yada. But that's me musing. So, with that said, it's time for everyone's favorite part. Homework. I know. But